I don't.
Okay, so I think we're out of time. Thank you, Quinton. Thank you very much.
Doesn't matter.
Okay.
Hello.
Just get onto your bed. Okay? There you go. And you're good to go. Can I borrow this from me? Introduce you. Okay, folks, can we bunch up from the sides to let more people sit down? Okay, folks, we're starting the next presentation. Okay. So I'm going to... Okay. So I'm going to introduce my good friends, Magnus and Bjorn, and they're going to be talking about AF XDP. Can we have some quiet from the room, please?
All right, let's get going. So my name is Bjorn Törpel, and this is my partner in crime, Magnus Karlsson. We're from Intel, as you can see from the nice blue. And we're here to tell you a bit about what AF XDP is. Was that? Is this better? Better? Okay. Okay, so you missed the word from our sponsor, but we'll skip that, right? Okay, so why are we doing this? So if you ask most developers or network application developers today, like you have to pick a platform and you have to pick an API. Most people say Linux and BSD sockets. So why is that? Well, it supports a lot of features. It's there. It works. People are familiar with it. So that's the pick. So say that this developer wants to develop a DPI application. That's Deep Packet Inspection application. And it goes to what's provided by the kernel, which is the AF packet socket layer. After a while, he realized that, okay, I'm not getting the performance that I like. So what can I do about it? Well, I can throw more cores at it, which is, I mean, we as Intel would love that, but it's not for everyone. So, and I mean, it might not even be possible to throw more hardware at the problem. So the typical solution then is to go to a hardware vendor. For example, someone that provides specialized NIC or some kind of specialized hardware. And the problem here is that usually with these hardware, you get a proprietary SDK. So you have to change your application, and if you want to try another hardware, you have to change the application once again. They're usually hard to use. They usually lack a lot of feature that Linux has, but this specific hardware doesn't have. But then there's software solutions as well, for example, DPTK, and there's PF-Ring and NetMap. They're really fast, but they're not really integrated into Linux. So again, it requires you to rewrite your application, and the biggest problem here is that it's not really integrated into Linux. So if you want to use the features from Linux, then you have to re-implement them yourself in in your software, and that's not optimal, doing things twice. So the problem statement is, so can we take the ease of use and features of Linux and the socket layer and combine it with the performance from here? And let's see. So what we're proposing is a new socket application. What we're proposing is a new address family called XDP. And it's a socket layer, and so you can view it as the user space part of XDP. And we just had a great introduction to XDP from our previous speaker, so I won't dwell into that. The solution is free from system calls. So the transmit path and receive path has 0 system calls. We also provide a new kind of allocator that if you modify the device driver and use this allocator, you'll get true zero-copy semantics all the way out to user land. So that means that the NIC will DMA the frame out to memory in the user space application. Okay? If you do not use this allocator and use an unmodified driver, you will still get a copy, but pretty good performance. Anyway. Last thing is that we do not expose any hardware details to the user application. So instead, we're exposing virtual hardware descriptors that are being translated from in the kernel to so the virtual hardware descriptors are being translated to hardware descriptors in the kernel. Yes. All right, one thing to note. So if you're using the zero-copy mode, then your hardware has to support hardware steering. So for example, we have 2 sockets receiving two separate flows. Then in order to use zero-copy out to user land, you must be able to steer the flows. But Magnus will tell a bit more about this later. Okay, so what else? Our goal is to hit 40 gig for large packets, 40 gigabit per second, and for 64-byte packets, we're hoping for 25 gigabits per second. All right, so from Linux perspective, why is this good? Well, we get a new socket layer that's fast, and we're hoping to be closer to DPK, or just some % off. You get out-of-the-box support for all network devices that's already there in Linux. So Linux support a whole lot of devices. What else? It states that XDP is required, which is not entirely true. To get the best performance, we require XDP. But it can fall back to a mode that's based on SK buffs instead of XDP, and so you can use the same application interface for all the device drivers, but some device drivers will have better performance, obviously. Okay, I'll wait with the future work for later slides. Okay, so from DPTK perspective, why should DPTK care about this? Well, say that you implement a Pulmo driver based on AFXDP. Then you can still use your DPTK applications without any changes. But instead of having the device driver in user space, you let the kernel handle the hardware, which is, honestly, the kernel is pretty good at that. So the goal here is to have, of course, there will be a performance hit, but we're aiming for 10%. And for some application, that might be good enough. As a follow-up, another good thing is if we leave all the user space drivers aside, then we can actually use DPTK inside containers, which is not possible today, at least not in an easy way. And another thing is that you don't have to re-implement things like scheduling and backoff in your user space application, because the kernel can do this. So we support, for example, the poll syscall. So we can first do busy polling, and then if we don't want to do busy polling anymore, we just back off using the poll syscall. So again, maybe the goal is to, if DPK is using this driver, then DPK can be seen as a really good packet processing library, which is currently is as well. So we think AF-XDP could work really good in conjunction with DPK. All right. All right, so enough talk. Here's the code. So you start off by creating a socket. You allocate some buffers using your favorite allocator. And the buffer is where the frame data will be DMA'd to. You pass this buffer pointer to the kernel, so you register the memory to the kernel. You create the virtual descriptor rings, the RX and TX for ingress and egress. And then you bind the socket to a certain interface. So you state, okay, I want to bind to this IF index and a specific queue in the NIC. And then in this example here, I'm using busy polling. So I read messages from the ring, I process them, send them out. So, and again, I can put the poll syscall in there if I want to back off. Right. So where does XDP fit within AF-XDP? So my plan was to do some introduction to XDP here, but I'll skip that. So what we've done is that we've taken the redirect action from XDP and said that you can on top of redirecting your frames to other net devices, you can redirect to an AF-XDP socket as well. So it's just another target for redirect. And somewhat crazy idea we have here is that maybe we can do descriptor rewriting from XDP as well. So we could, from XDP, support another descriptor format, for example, VirtIONet. And then we could do virtual machine networking using the AF-XDP socket layer. What else? Right now, the current patch set only consumes the frames, and the received frame that are being redirected to a socket is consumed. But we will need to be able to copy the frame to a socket and then pass it on to the stack, because then we will have TCP dump could be able to use that and have a much faster TCP dump than the current AF packet-based one. And also I've been discussing with Jesper down here about doing load balancing from XDP program, so we can receive a frame and then load balancing it over multiple sockets. Right. Yep. And just a few notes on the operation mode. So if a driver is unmodified and doesn't even have XDP support, we support something called XDP SKB, which is a mouthful. But that means that you can still run your XDP programs. It'll be slow, obviously, or as slow as the SKB path is. But it will work. So you can use that on any device or any net device driver, any net dev device from the kernel. If the device driver has support for XDP, then you use the mode in the middle, and that's still copy, but it's much faster than the first one. And finally, there's the modified driver that's using the zero copy allocation scheme, and that's the fastest one. All right, so I think I'll pass on to Magnus.
Okay. So how do we do this zero copy stuff now? If you look at the picture on the left-hand side there, that's the classical non-zero copy case. In that case, the TX and RX descriptors of the hardware ring is just mapped to the kernel. They're not visible to user space. Same thing with a packet buffer, only visible to the kernel. What Linux does then is just copy out the packets into user space. And with the TX and RX descriptor, it just translates those into some hardware agnostic format that's in user space. And that's a good thing. I mean, operating system is about hardware abstractions, security, robustness, isolation. You get that here. So we want to keep that in our zero-copy solution. So that in the zero-copy solution, we do not expose TX and RX descriptor hardware rings into user space. They're still translated by the Linux kernel into some format, which looks different than other sockets, but it's still a hardware-agnostic format. And, it's going to be secure and isolated and stuff. But the key difference here is that we take the packet buffer and map it straight up into user space. So packets from the NIC are mapped by DMA straight into user space. If you have two applications here, two processes, note that the RX and TX descriptors are never, ever shared between these two processes. Packet buffers, on the other hand, can be shared. By default, they're not shared, but if you like shared memory, there's nothing that hinders you to share the packet buffers. Of course, you create a huge fault domain. The other process might actually pollute your data and so on, but yeah, you chose it. That's what you get. But it's possible, but never with the descriptors there. Hit the next one. Yep. Okay, so security and isolation, that's very important. So what are the requirements here? So we make sure that, user space can never crash the kernel or another process. And also that it cannot read or write any kernel data, which is, of course you have to know it. And you cannot read or write any packets from any other process. So what do you need in order to do this? Let's say you have two processes at this point, A and B. And all your traffic goes in through a single interface. So you have to split up the stream of traffic to process A and process B. And if they have like AP address X, AP address Y, then you actually have to use some hardware steering in order to steer this packet. That's a requirement for untrusted applications, multiple untrusted applications, where the flows come in from the same port. Because otherwise, you couldn't just take that flow and just push it up into a single untrusted application and have that spread it out, because then it would be able to see any packet and modify any packet. So that's not a good thing. So, but fortunately, since like 10 years ago, most NICs actually support classification. And if you look at NICs today, they're becoming more and more advanced, and can do more and more stuff. You can even download XDP programs into network stuff. So they're becoming more and more flexible. So I don't think this is a problem. But there's always going to be, in some cases, something where you can't perform the classification in hardware. And in that case, you have to use the XDP SKB mode or the XDP driver mode, which copies out the data into user space. And then what we want to achieve is having then the classification being done in XDP. So you download your XDP program, it does the classification. Of course, it's going to be slightly slower, but still a lot better than before. Okay, let's look at some numbers. So we have this experimental setup here. It's the latest RC that came out Wednesday, I believe. No, Tuesday. It was even. It's just on some Broadwell server here. We use only 2 cores to these simple micro benchmarks here. And the app runs on 1 core. And then I know this is completely brain dead, but TX and RX runs on the same core. Of course, that's not good, but we're going to fix that. It was just a faster way to get to this point. TX, of course, should run on its own core, but it doesn't at this point. So they will compete, as you will see in some of the benchmarks where we use both TX and RX. We only use 1 queue pair. It's a 40 gigabit 412 NIC. And we use an XLO generator blasting it just for 40 gigabits a second full traffic all the time. We have 3 micro benchmarks. We have RX drop, which just receives the packet, doesn't look at the data, just drops it. TX push is kind of the opposite. It has pre-computed TX packets. Just try to send them out as quickly as possible. Only RX, only TX. And L2 forward is then receive a packet, swap the MAC header, send it out again. So this actually does touch the data. And we have 4 different columns here. We have AF packet v3 that exists already in Linux. And then we have the 3 modes that we have introduced. And the first thing that you can see is that, well, even this XDP SKB mode, which works with any, network device, it's like 2 to 5 times as fast as the previous fastest one. And we compared V2 and it's similar to this, so there's nothing special with V3. So that's pretty good. That works on anything. And it gives you, pretty much the same. It's a raw data interface in both cases. I think that's good. And then we have the XDP driver case, which is going to work on any driver with XDP support. And with RxStop, you can see it's like 15 times faster than V3. I think that's also really good. You can see that there are dashes on TX push and L2 forward. So that's one of the challenges we had with this RFC. We couldn't reuse the XDP TX NDOs in the driver. But I think that's going to be worked out. So hopefully we'll get to some change to those NDOs where we can actually use, have a mode for this even in TX here. So we'll get some numbers here, but the code is not ready. But even better performance you can get with the zero copy one. We start by just looking at TX push, it's about like 22 times what you have here. And RxStop on the other hand, it's like 17, or that's also not 20 times. But something to note is that, I mean, we had a previous version of this, which we called AF Packet V4, just the new version of AF Packet. And it actually had like 40 times the performance. The reason for that is that we have done absolutely no performance optimization on this code. It's just there for functionality. While with this guy, we actually did some performance optimization. So my guess is that there's lots of low-hanging fruit to be had here. So these will definitely increase. We have spent no time on performance optimization this. So the goal is to get it at least above 30 million packets per second for these 64-byte packets. But still, clearly, we have work in the optimization area to do. But I think, you know, all these numbers to me look promising. There's lots of future work that we can do. I'm going to see we have 9 minutes. Of course, we have to do the performance optimization work. And really something very important, and it's a call to you guys. If you have some real workloads, please try them out. I mean, you know, I had toy micro benchmarks here. It's very different from real workloads and those toy micro benchmarks. If you want to try it out, the RFC is on the mailing list. Just download it and, you know, let us know what works, what doesn't work, please. We really want to make the syscall. We have a syscall on the TX just to get it going. We'll try to get that, to get rid of it, and also to get TX off the RX core. Because, I mean, you saw that performance of the L2 forward. I mean, it's limited by RX and TX competing on that core. Of course, that's not good. But we'll fix that. Packet steering using XDP, talked about. Also, I mean, XDP has metadata support now. It would be nice to tie it into this so you can get metadata. Maybe it's hardware offload stuff, or it's things that the NIC had already pre-computed for you, and you can, you know, get that up there. Also, I mean, let's say you start an application, you bind to a certain NIC and you bind to a certain QID. Let's say QID 100, and then you run it on another NIC. It doesn't have a QID 100. You still want that program to work. So you should be able to emulate that QID by some, you know, copying or whatever. Today that's not supported, but really want to be able to have the same program working on every single NIC, you know, independent how many queues it has. We also would like to see an XDP redirect to other net devices RX path. Today you redirect it to the TX path and send it out again. But it makes a lot of sense in certain cases to actually redirect it to the RX path and upwards again. Today there's only, at least in the previous kernel, I haven't looked in this one, you correct me if I'm wrong, yes, but you only have one XDP program for the whole, your whole NIC. You don't have it per queue pair. But here, if you can open an AF XDP socket per QID, it makes sense to have an XDP program per queue pair. You can do this today by Jesper's patch. You can have one XDP program and filter stuff out on QID in your XDP program, but it's still easier from a management point of view to have these as separate programs instead of just one monolithic entity. And somebody talked about, wasn't that a question about XDP support on TX? I mean, yeah, eBPF has TX support, but XDP doesn't have it. But it makes a lot of sense to have it, especially in conjunction with this AF XDP sockets, to actually be able to execute an XDP program on the TX path too. That's not in place today. And the queues are really single consumer, single producer, just to be as fast as possible. But there are use cases where you really want them to be multi-producer, you know, single consumer or even single producer, multi-consumer. So it would be nice to be able to plug in such a ring into it. We have tried to write the code so that the ring structures are completely abstracted away from the rest of the code. You can actually plug in different ring structures. So it would be nice if somebody could try this out. And the clone packet configuration, just to be compatible with AF packet. The AF packet today, it clones the packet, sends it out to user space, and another one is sent through the stack. We want to be able to do the same thing to support like TCP dump, Wireshark, and these things. And in the previous version, we did a TCP dump implementation that took, only took 3-4 hours to convert the TCP dump, and we got 20x performance improvement on TCP dump. I think that's decent for 4 hours of work. So we want to be able to do something similar here. Right? So we've got 5 minutes. Okay, conclude. So we introduced this AF XDP, formerly known as AF Packet v4. It's integrated with XDP. It's basically the user space interface of an XDP program. And the zero copy, we have it up to 20 times now. We had it up to 40, but the current patch set is 20. So we hope it can be even better than this. And there's an RFC on the NetApp mailing list. Please check it out. It has, of course, all the details. This is just an overview. But there's still lots of performance optimization work we need to do. It's there for you to look at, and it's there for just getting the design out for you to comment on. It's not there because it has the greatest performance on Earth yet. You shouldn't start to optimize performance before it's ready, as we all know. But it's very tempting. Of course, and we also think there's lots of exciting XDP extensions to be had in conjunction with this. And to hit the one, I'm not going to go through this, but there's a couple of people in the audience that we want to thank, and more people here. The RFC you can find here. Okay, questions?
Go ahead.
If I have to write an application with an API, I can make a choice with DK or using your XDP API. Why would I choose one or the other?
Yeah, okay, so if you started from scratch, you made a choice, what should I do? So it depends on, if you, for example, had very, very tight performance targets, or you were making an embedded system in an integrated box, then I would probably, you could probably go with DPDK, especially if you had different deployment scenarios. You wanted your code to run on both the embedded system, a box, you wanted to run in the cloud, you wanted to run on somebody's server, then go with DPDK. You could deploy it anywhere, for example. There are many other things too. DPDK supports offloading. We don't do that at this point, and so on. And it doesn't have to be an either-or choice either. So.
So, how much similarity do I have for application compare DMAs with XDP? Because both seems to be very close from the semantic and system code. So
That's a good
it
question.
reminds me RDMA APIs, but for describing.
You know RDMA.
Repeat the question.
Okay, repeat the question.
So the question was, why not RDMA?
Yeah.
It's a good point. We actually started out looking at that. And I think the main thing is that it's so different from what's in the networking stack. In terms of, but, hey, it might be a good fit.
But lots of things were inspired by RDMA. You know this.
I want to avoid having two things to support from the kernel.
Yeah.
Right, yeah. And it's, this is my subjective opinion, but it's a bit too much, I'd say, for most applications. RDMA is for all the storage things that are too much, but might be.
With RDMA, we have some offloads.
Right. And it's RDMA has been around for a long time, so it's really mature as well. But
There's like two people waving.
yeah, one more.
Right.
So you mentioned multiple processes dealing with the same data stream. In the case of that, do all those applications need to essentially try and process the data as quickly as possible? Otherwise, is that the design method you've chosen as opposed to buffer referencing or something? So just to give you, we do this with NetMap quite currently. So is that a similar idea for all the applications? If one of the applications is running too slowly, we'll block all of them. Is that current design?
No, I didn't. So,
Yeah.
If the process is processing a single data stream and one of them runs too slowly, will it force packet drops on all of them?
okay. Yeah, the question is how you design it, but let's take that offline. Sorry, thank you.